Okay, so this unit on functions is very, very repetitive in a way. Most lessons, or most weeks, follow the same pattern. I'll start with an intro day, where I'll introduce a topic. We already kind of did that for exponents. Then we're going to talk about graphs and what they look like. Most of those lessons are called characteristics of blank functions. We'll talk about their properties. Today, characteristics of exponential functions. Next week, characteristics of logarithmic functions. Week after that, anyways, that's the point, right? Sometimes we also will spend a day talking about how to solve them as well. But most of the time it really involves, here's an equation, here's what the graph looks like. Tell me about the graph. So let's just do a quick little bit of review based on some of the graphs that you should already know. I'm going to close that direction. Okay, so this slide right here just has a whole bunch of generic functions on it, some of which we actually do in this course, some of which we actually don't do in Dash 2. They do in Dash 1 though. Here's a constant function, basically a straight line flat across. What's the domain of a function like that, Cole? Hi. You're not listening. No, you're not. So I picked on you. Element of the reals. Here's a linear function. Domain, element of the reals. Square function. Quadratic function. Element of the reals. Cube function. Element of the reals. By the way, if you haven't figured out by now, if I haven't said this before, the domain for so many graphs is the element of the reals. However, it's actually not this week, but next week when we do logarithms, that'll actually change. But at least for right now, it actually stays that way. The range of these graphs is sometimes even element of the reals. Or sometimes it's actually not x, it's y. Sometimes though it's like y is greater than a number, like say greater than 0. So hopefully you're fairly comfortable with being able to graph a polynomial, look at the graph and tell me things like domain, range, intercepts. Which quadrants does it go from, like quadrant 1 to quadrant 3 or something like that? Could you tell me what degree the function is? Well, we're going to do the same thing now, only we're going to talk about exponential functions. So without further ado, let's hop into it. We can do linear quadratic polynomial. Just so you guys know, rationals is actually for my Dash 1 class. So we don't actually have to do that. We can cross that out. We don't graph rationals. That being said, we do work with rationals. Like an equation you guys would have had before would have been 3 over x plus 1 equals x squared plus 3x plus 2 all over x plus 2. You guys remember doing this from our first unit?
Yeah.
You don't have to graph these things, but you do have to know how to work with rationals as part of Dash 2. So let's give them a try. We're going to try graphing this graph, and then we'll talk about some properties. So grab a graphing calculator. On, let's see, what day was it? Thursday? Thursday, we did a little bit of review talking about how exponents work. 2 to the power of x really means 2 times 2 times 2, and I'm never allowed to stop. Ever. Well, at least unless I tell you what x is. If I tell you that x is 7, then it's 7 x's, 7 2's times by each other. So the way you'd graph that, normally what we'll do is we'll write the 2 in a bracket, and then we'll put an x, but you can probably skip the bracket. You can just go 2. This little button right here makes it the power of x. That's what we want to graph. You may have a calculator that actually hops the little x like up top. If you have one of the newer ones. Anybody have one of those ones where the x actually kind of goes up to the top? Okay. If not, then just do what I have here. And let's graph this thing.
I did not get that.
Did not get that. Okay, let's troubleshoot. Okay, so actually, let me troubleshoot a few common errors first. Okay, common error. This is Latoya's error. Go back to your y equals screen. If you still have plot 1 turned on, you're graphing the last question you did. Okay. Make sure you go back to like a nice zoom standard as well, a nice 10 by 10 graph. Okay. So then we also want to do zoom 6 of standard to get to a 10 by 10 graph. Because your window size was wherever it was.
Dang it, like that doesn't look hard.
Got it to work?
Yeah.
You guys get it to work?
I got it.
Okay. So let's talk about some properties of this exponential graph. First and most important property I want to talk about is that y-intercept. Well, if I want to find it, I go second calculate the value when x is 0 to find that y-intercept, and it's at 1. And this is something that we talked briefly about on Thursday. 2 to the power of 0. If you have no 2's, it doesn't mean you actually have nothing. It means that it's like 1 times 2 to the 0. It means you have the number 1. So your y-intercept is at 0 and 1. But along with that really important property, there is no x-intercept. This is not possible, like NA for not applicable. Here's the reason why. Remember from Friday, 2 to the 1 is 2, and to the 2 is 4, and then 8, and then 16. But if you do negative numbers, 2 to the negative 1 is 1/2. 2 to the negative 2 is 1 over 4. 2 to the negative 3 is 1 over 8. This graph will continue to get smaller and smaller and smaller, but will it ever reach 0? No. I think I gave an example of someone getting divorced and losing half their stuff, and then getting remarried and then getting divorced again, losing half their stuff, and then repeat that process. If you keep losing half your stuff, you still have stuff though. You just don't have as much of it. Can you have negative stuff? No, I mean, you're still losing half, right? This graph will never, ever, ever be in the bottom quadrant. Actually, I'll show you how we can put it in the bottom quadrant later. But for starters, though, this graph is not in the bottom quadrant. It can't be. You can't somehow end up with a negative number down here. So this graph usually has roughly this sort of shape where it just kind of takes off. Now, do you guys see how my graph right here, it looks like the graph kind of stops right about there where the cursor is? This is because your calculator is drawing the line literally on top of the axis. So you have to make sure that you actually continue drawing that line all the way to the back. And I'd prefer if you put an arrow on it indicating that this graph does keep going in both directions for forever. So don't draw this. Let me show you what I don't want you to draw. Don't draw that. If you just draw that, it means that you can look at a graphing calculator and draw a picture, but I'm going to need you to have a little more understanding of what's happening. The graph doesn't just start all of a sudden randomly right where this eraser is. The graph is still going down by the axes. It's so close to the axis right here that it's like drawing it right on top of each other. So that's why you don't see anything. If you'd like to see the graph there, I can show you a trick. Go back to y equals. Press the backwards arrow until you're hovering over top of this little slanting line, and press enter once. And it should make that line be a dark, thicker sort of line. You guys find that? And then regraph the thing. And what you should see now you can see where that thick line happens to be all the way across the axis.
It's kind of like on the bottom.
It is. I think that's because the line is particularly thick, that's all. Because it's actually not technically below 0. It's just you've made your line quite enlarged. Did you get it work?
Oh, yeah.
Okay, you just practice shading stuff. Okay. Okay, let's talk about a few other properties here then. Exponential graphs, like with all the graphs we've had before, the domain is x is an element of the reals. You can use any x value you want. And honestly, until we get to logarithms, that's pretty much always true. I can't think of an example yet where it wouldn't be. But just so you know, domain will not, that's not always true. Anyone want to hazard a guess as to what the range is? It's not, because down here, can you get a y being negative? Think of quadratic. Sometimes quadratic graphs don't go that low. This graph does not reach -7. It doesn't reach -6.
It has to be greater than or equal. It has to be greater than 0.
Good, you caught yourself. It has to be greater than 0. Not equal to, though. Because, like I said with that losing half your stuff in the divorce example, will you ever have 0 of something? Well, no. If you keep cutting things in half over and over again, and you have 1/4, 1/8, 1/16, 1/32, eventually you'll have like 1 over a million. Is 1 over a million actually 0? Not technically. Super darn close to 0, but it's essentially 0, but it's actually not 0. So you cannot put that little bar underneath there. And that's actually something very common they might throw in a diploma question. They might ask you what's the range of the function. And they might say like A is y is greater than 0, and B is y is greater than or equal to 0. So make sure you're very careful, because that little bit of notation makes a difference. There is a new characteristic that only fits these graphs, and it's called an asymptote. And an asymptote basically describes what we just talked about. The concept about how if you take half your stuff, and half your stuff again, and half your stuff again, do you still have stuff? Yeah, I guess. But really, you're getting closer and closer to 0. Well, an asymptote describes where a line is getting very close to but never actually reaches. This line right here is getting very close to 0. But does it ever actually equal 0? No. So what we do is we call it an asymptote. An asymptote is the equation of what the graph is getting really close to. And I'd say the graph is getting very close to the point where y equals 0. Does y equal 0 though? Technically no. But is it getting very close to 0? Hopefully you'd agree. Yeah, it's pretty much hovering right parallel to it. One more thing we should talk about is the end behavior. Which quadrants does this graph go from?
2 to 1.
Yeah, 2 to 1. Yeah. From 2 to 1. Which, by the way, is very similar to a quadratic graph that goes from 2 to 1. Does that make sense? Because a quadratic graph can do that too. The only difference is this graph does not end way up high in the air like this. This graph basically like it flattens out along the bottom. That's your basic exponential graph. Any questions? So from quadrant 2 in this one to quadrant 1 in that one. Okay, let's try another one. This is the graph of y equals 3 to the power of x. So really the only difference is change the 2 into a 3 and look at the graph. Did it even really change?
No, literally everything's the same.
It's not perfectly the same. Let me just compare the two. You guys don't need to do this, but I'm going to throw on 3 to the x as my bold graph. I'm going to put 2 to the x as my not bold graph, just to compare. You guys see the slight difference between my two graphs?
Yeah.
The 2 to the x graph is the regular thin line, and it does kind of rocket ship up. But like the 3 to the x graph just kind of takes off just a little bit steeper, that's all. The 3 basically is kind of like the slope of your graph. So in terms of properties, let me go back and just remove this one. The properties are all almost the exact same. Where is your x-intercept? Good. Will this graph ever cross? No, it can't. You can't take a third of something and still have negatives. The y-intercept is at 0 and 1 though. And you can test this if you wanted to. But I know this to be true because 3 to the power of 0 means you have no 3's. Right? But essentially what's happening is it's 1 times 3 to the 0. You have 1, and then how many zeros are you allowed to have? Well, you're not allowed to have any zeros. So what are you left with? You're left with 1, technically. Not left with 1, 0. You're just left with the number 1. So what's your domain? Anything you'd like it to be. Yeah. That's not going to change yet. What about your range?
Would it still just be greater than 0?
Yeah, because it looks like this graph sure is kind of flattening off there at 0, right? So it's greater than 0, not equal to, which is greater than 0. Based on that, what does the graph getting really close to? 0. So we usually write asymptotes as equations. Y is going to equal 0 is your asymptote equation. And your end behavior is from quadrant 2 to quadrant 1. Honestly, this graph really hasn't changed much at all, has it? There's one more thing that you might say about this graph. You might say that this graph is ascending. Or you might say that it has growth. Because I'm going to show you an example in a second of a graph that is not ascending and growing, but is actually descending. I'll see if that's my next one. I hope it is. I hope I structured this right. It's not?
I don't think so.
No, it's not. Okay, we will eventually do that. But let's try this next one. Okay, this time around, the bracket is going to be very important. Because what this means is that this 2 is repeated X number of times, but there's a 2 in front of it that you only get 1 of. So write it like this. 2 bracket 2 to the power of X. It does look the same. So you might be tempted to say, hey, let's write down all the same properties. There's one in there that I'm using to make a point.
The y-intercept.
It's the y-intercept. Good, yeah. So let me go through them one at a time, though. With that same process. So the graph does this whole taking off like a rocket ship concept. Does this graph go below the axis? No, there's no x-intercept. But your y-intercept is 2. Let me explain why. First, let's prove it. Second, calculate the value when x is 0. And now it says it's at 2. Why is it at 2?
Because there's a 2.
Yeah, it's this 2 right here. Let me explain how this graph works. This graph is supposed to be 2. Then we times by 2 over and over again, an unknown number of times.
So that's your class.
But how many times are we supposed to times the 2 by? 0 times. So you're not supposed to times that second set of 2's by anything. So if you're not having any of these 2's right here, if you have none of those, what's left? A 2. Does that make sense?
Yes.
So your y-intercept is at 0 and 2. But the good news is almost everything else is still the same. Your domain, yeah, you can use any x number you'd like. That's usually pretty typical. Your range, well, it just has to be bigger than 0 because you still can't have negative numbers. Asymptote, yeah. The one thing that it can't be is 0. By the way, let me show you that in a table here. Go second, calculate, and do like your table. Anybody ever played around with this before? I'm just going to go upwards. It's like 0.125, 0.025. As I keep going upwards on my graph, these numbers here keep getting smaller until I get to like 0.0195. And then after 0.0195, it's 8.9 e minus 4. Well, that just means 0.0000. Like it basically means a lot of zeros in front of the number. So as I make my x numbers become very negative, my y values become very small. So, okay, last thing in behavior, from 2 to 1. Can you guys handle graphing like something like this?
Yeah.
Very similar to what we've been doing. I think in a way you'll like it because it's just adding a new function to the list. Let's not graph this one then. Let's just talk about the properties. If I put a 5 in front, what is the only thing that will change? Yeah. Does that make sense? So, x-intercept, not possible. Y-intercept on this one should now be 0 and 5. Purely because there's that 5 in front. 5 times no 2's leaves you with 5. Your domain is an element of the reals. Your range is greater than 0. And it's probably from quadrant 2 to quadrant 1, because I bet you the graph looks like this again.
No way.
No way. Okay. Very repetitive, isn't it?
No.
Okay, let's change it up a bit.
Oh.
So we should graph this one here. This is a 2 in front.
So if we skip that last one?
Yeah, I just kind of skipped over the one with the 5 in front.
Let's do.
So we need to go y equals 2 bracket 1 over 3. Close the bracket. Then arrow power of x. So you need this guy typed in.
Yeah, that's on your side.
Boom.
What happened now?
It's on the other side.
Yeah, the graph is actually descending. We have a name for this. We call this either decay, or you could call this a descending function. Where this graph is going down. The other one was going upwards. This one's going down. Anyone want to hazard a guess as to what characteristic of this equation causes that to happen? The fraction, yeah. If you ever get a fraction right here, like a rational, so rational is a good word too, right? If it's a decimal number, it's going to make the graph become smaller and smaller. This means keep a third of your stuff over and over again. So, okay, so what's the x-intercept?
Not applicable.
Still doesn't apply. Still can't find one. The y-intercept, though, should be 2, hopefully. When you guys graph this, if you want to test to see what the y-intercept is, you can do that. But I'm hoping you'll discover with some practice, it's this number right here, that 2 in front. Take 2 and times by 1/3, never. So then you just have 2. So domain, element of the reals, range, greater than 0 still. That hasn't changed, actually. This graph still gets really close to the axes, so it's the y equals 0 asymptote. And it goes from quadrant 2 to quadrant 1, but I want to point out it does it a little differently. Rather than going up from quadrant 2 up to quadrant 1, it starts high and comes downwards. So just make sure that you're aware of that being a decaying, decreasing graph. Does that make sense? Okay. Well, at the end of the day, that's essentially what we have to do. We have to look for those properties. But there's a few other graphs we're going to do a little bit later here where we can mess around with that. This is more or less a summary slide, though. A basic exponential function looks like one of these two things. Either it goes up and it grows, or it goes down and it decreases and decays. Those are the two possibilities. I also want to show you guys this one. And this one seems kind of weird. So I have to give you a little bit of backstory to this one. You are going to get tested on the diploma on something that's not in -1 curriculum. It's very odd. This is actually a calculus thing. And for some reason, they throw it on the -2 diploma. I think it's ridiculous. That being said, I don't get to control this, so I just have to teach you it. Yeah. So I need to give you basically the 5 minutes or less version of a really complicated calculus topic. I promise you this is not really that hard, but we have to use the number e. We say that again. We have to use the number e.
2.7.
Yeah. Do I have a slide about that on the next one here? Let's go to that slide here. E is actually a number. And this is, like I said, this is what like Delver and Harris are going to be doing in calculus. I don't even think they're that far yet. And yet, we teach it in -2, which is silly. Actually, no, they did do this, because I talked to them about this. But E is essentially a number. It's like pi. You know how pi is 3.14159, blah, blah, blah? Well, a really smart scientist, mathematician named Euler. It looks like Euler, but you actually pronounce it Euler, like the really, really bad hockey team. Anyways, Euler discovered this number called E. It's called the natural number. And I think the reason for it is that this number here has been found in a lot of like real world scenarios where when things grow naturally, they grow according to this number. Okay. Long story short, what I need for you guys to know is that E is a number and it's in your calculator. Okay. If you want to look for E, go second, divide by sign, and you can see this little E right here, and there's your number. So essentially, it's kind of like pi. And it'll graph just like the other one. So I find it dumb because honestly, this is actually calculus. Like we use it in calculus. That being said, for what you guys are going to be tested on, you just have to be able to use that as a number. So if we were to graph it, it'll be y equals e to the power of x. And it looks just like every other graph that we've done. E is about 2.871. Okay. Before we move off past E, I need to give you guys a little more context here as to why we need to learn about it, even though it's kind of dumb. It's called the natural number. Okay, and the reason why it's considered natural is that many real-world things we've discovered seem to progress at this rate. One of them, for example, would be like, say, how a bee population would grow over time. Okay, it doesn't double, it doesn't triple, it's somewhere in between that rate. If it were to double, it would be 2 to the power of x. If it were to constantly triple, guys, can you focus, please? If it were to triple, it would be 3 to the power of x. But there's a number in between there that's this 2.71 number. And it seems to be what a lot of natural things will double / triple at. It's just, it's not a whole number, that's all. I have a slide in here talking a little bit about the calculus behind it. I don't need you to know this, because it's a little bit intense. But this is how Euler came up with his number. 1 plus 1 is 2. Okay. 1 plus 1/2, but to the power of 2. So you know how like this is a 1? We'll make it go to the power of 1 is 2. Make it a 1/2, but then put a 2 here, it's 2.25. Make it a 1/3, but put a 3 here, it's 2.37. Well, he kept doing this over and over again. 1 and 1/10 to the power of 10th is 2.59, until eventually you kind of recognize that 1 over 1,000th to the 1,000th ended up giving you 2.71. And this is like a sort of like a common sort of pattern that Euler discovered. So, long story short, E is now a number. Just go with it. It's not really that hard. Okay. Now I'm going to throw a monkey wrench into things. So focus still if you can. Do you guys need a break?
Yeah.
Would that help?
Oh, yeah.
How much longer?
Well, let's look at that first.
Only like 3 pages left. Okay.
Can we
Finish it off and then.
finish it off and take a break?
Yeah.
Okay.
Break.
Okay, so here's another twist. Look at the equation here. What sort of things are different about this twist? Do we have an exponential function? Is the exponent an x? Okay, there's the first thing. It's an x plus 2. That's going to mess with things a little bit. There's also a -7 afterwards. That's also going to mess with things a little bit. So let's talk about how to graph this. If you have a calculator like mine, you have to do this. Bracket 2, close bracket. Then go to the power. Then you have to open a new bracket for all of the exponent of x plus 2. And close that bracket. If you have Thomas's calculator where the little x plus 2 goes up top, just make sure the x plus 2 is up top, okay? Then bring the cursor back down because then you have to -7.
Oh, this is crazy.
And now our graph has changed a little bit. Now it starts in quadrant 3. So this is the last little twist. You have to be able to deal with the fact that the graph could be messed up a little bit. Does it still have the same rough shape where the graph is flat and then goes, takes off?
I did not get that.
You didn't get that? Okay, let me troubleshoot.
That's what I got.
No.
This camera, I got that.
Okay, we need just regular old subtract.
Second.
Because you're subtract 7.
And then you find the.
Anybody else having issues getting that, or we got the graph to work?
Oh, no, I already got that one.
I got it.
Okay.
The x-axis.
And
One
what
is the
is
x is representing 0. The y is a 3.
Guys, can I work through this with you guys now?
Yeah.
So I'm going to talk about a few of these properties. This graph more or less looks like it's going straight flat across here,
And then it just kind of.
and then it takes off like a rocket. So hopefully it will look something like this.
Does the domain change?
Well, let me do them one at a time, okay? So first question, does it have an x-intercept now? Yeah, now this graph should have an x-intercept. So second, calculate the 0. Put this on the left and on the right. And it actually can have an x-intercept. It doesn't have to, but it does at 0.807 and 0. That's different. Didn't used to have that before. Is there a y-intercept? I think there is. It's got to be right about here. To find a y-intercept, second calculate the value when x is 0. It's at -3.
Mine's -3.
Sorry, yeah, -3, right?
Yeah.
-3? Yeah. So -3 with 0. By putting a little x plus 2 right here, and by putting a -7 right here, it buggered everything up. Because otherwise, I would have said the value should have been 1 because of that 1 right there. That kind of changes things. Okay, the domain, by the way, is x as an element of the reals. Can you plug in every value for x that you want? And I have no reason not to. Eventually, we'll talk about graphs that there are restrictions, but as of right now, could you plug in x being 5? Sure, that's right about here. Could you plug x in as -1? Sure, that's right about here. Could you plug in x as 4? Sure, right about there. So every number is valid. It's your range that's a struggle. To figure out the range, here's how I recommend we try that. Go second, table. You're right, actually, it is -7. And the reason I'm going to know that is if I go to my table, do you see how where I'm at right now? It's about -6.9, -6.9, -6.9. But it doesn't go past -7. Look how it kind of just sits at -7 as I keep going backwards into the negatives. So your range is y is greater than -7.
So what was the asymptote?
But it's not actually equal to -7. You're right about the asymptote. Give me a second. Your calculator has given up. Right over here, it's actually 6.99999 repeated. And your calculator has basically given up writing all of these 9s. And at some point it said, guys, I'm just going to call it -7. Does it actually reach -7 though? The answer is no. Just like it never reaches 0, this graph will never reach -7. It gets to like 6.9 repeating. So again, do not put that little bar underneath there because it does not equal to -7 ever. Because that's its asymptote. Y will get really close to -7, but even though your calculator claims that it equals -7, it doesn't. And I have a way of proving that to you. I have a way of proving. Go to y equals, and on a new graph, like y2, type in -7. And then go back to the graph. And it should make a line that looks like these two lines meet up right here, right? That's what it appears to do. If I were then to go second calculate the intersect and try to put the cursor over here where I think they cross, so maybe just watch mine here. I think they cross right about over here. Your calculator will think, this little thing up in the corner here means the calculator is trying to think. And using its little calculator brain, it is trying its hardest. And it says, I can't. The error message it gives is no sign change, but basically it's saying, guys, these two graphs, they don't ever actually cross. They don't touch each other. So the graph will never get as low as -7. Last thought, end behavior. This is quadrant 3, 2, 1.
Would you put the 4 in between?
No, I would just like you to put down like the quadrants that it goes from and to. But I guess you could. You could say it goes from 3, then to 4, then to 1. Like, I wouldn't call that wrong. But I've seen on the diploma, they might ask, like, one of the questions might be numeric response. It might say, which quadrant does it start in? Which quadrant does it end in? What's the value of the y-intercept? And what's the degree, maybe? And then you'd say, well, it starts in quadrant 3. So you put a 3 here. It ends in quadrant 1. The y-intercept was -3. And actually, the degree of this graph, this is a poorly chosen example. What is the degree of this graph? What is the largest exponent?
2.
Yeah, it's x plus 2. Do we know what x is?
No.
X can be anything. We don't actually do degree for this particular graph, by the way. Exponential graphs do not have a degree because the exponent is the number we don't know.
Got it.
Okay, I think we should take a break here. Before we do, though, I want to talk about the last thing I got to show you. Lost you on that one? Okay. The last thing I want to do is talk about the fact that you're going to get a word problem. And you're going to get one of these, you know all those buttons in your graphing calculator type things? You're going to be asked one of those. I don't know whether on the diploma it will be exponential or sinusoidal or linear or quadratic, but I guarantee you they're going to give you one of these things where you have to type number into lists. And chances are it's going to be associated with a word problem because they've also said that they're going to give you word problems. So the last examples I have, this one and this one, are both word problems. But why don't we take a break first? Because word problems usually take a little bit longer, if that's okay. So take a 5-minute break, and then we'll do our word problems. Okay, so why don't we do this? Rather than me go through this next section with you guys, you should hopefully know how to put data back in your calculator, because we've done this before. Let me say this. You are going to get regression of questions on the diploma, and they're probably going to be word problems. The biggest issue is it's a whole bunch of button typing. There is no work to this. By the time you're done, you're just going to tell me what this answer is, what this answer is, and what this answer is. Like, there's no work to it. So why don't I let you guys try this instead of me forcing you to go through it with me? And then when you're done, just call me over. I'll double check and make sure you have it right. Does that work?
I kind of forget how.
Sure. And like I'll come work with you one-on-one.
Yeah.
Does that work? So why don't I end the lesson here? You guys try the last 2 examples. And if you feel like you got a sense of it, then start either on your assignment number 8. Do some practice questions in the work journal, like the duotang thing. Or if you're behind, please get caught up because you're starting to dig yourself a ditch you'll never get out of. Okay?
Did you already do that for some of the math one?
So let's start.